The membrane controls the entry of nutrient and the exit of wasted products. It can generate difference in ion concentration between the exterior and interior of the cell, and also acts as a sensor of internal signal, allowing the cell to change in response environment cue. Okay, so you have here two cells, the prokaryotic cell and the eukaryotic cell. So just to, you don't have only the plasma membrane. So the plasma membrane, the surface of this membrane, it's around 700 micrometer square. But the internal membrane, it's the surface, it's tenfold higher. Okay, so it's 7,000 micrometer square. So you don't have only the plasma membrane, you have also internal membrane. You can see that especially in the eukaryotic cell, where you have the endoplasmic reticulum, the mitochondria, it's made by also membrane, so the cytosol and so on, lysosome and so on. Okay. So here you have the cell, the extracellular fluid, the nucleus. So it's made also by membrane, and you have the cell membrane, and inside the cytoplasm. So you know what is the size, the thickness of a membrane? What is the thickness of the membrane? It's around 4 to 10 nanometer, okay? So you have in this table the composition in weight, mass weight percentage of the component of the membrane. So you can see that protein and phospholipid are the main component of the membrane. Here, the membrane is made by a phospholipid bilayer. So you have two layers composed by phospholipid, but also composed by other, we will see that, sterol and proteins, okay? So the main components are proteins and phospholipids. So we'll start with the phospholipid. So the phospholipid, it's like this. You have an hydrophilic head, this. It's a hydrophilic head, and you have a hydrophobic tail. Which made by the carbon chain of the phospholipid. So you remember how we call a molecule which has a hydrophilic head and hydrophobic tail? It's called
amphiphilic.
Yes, amphipathic. I don't remember if you have an H. Okay, so when these molecules are assembled together, they can form micelle, bilayer. So this is the cell membrane, and also liposome. So liposome, it's a bilayer, but it forms a sphere. Inside, you have an aqueous cavity, and outside, you have the contact with the water. Okay. So you have, for the phospholipids, three common types of membrane lipids. So the glycerophospholipid, sphingolipid, and the sterol. So here you have, we will see after that, phosphoglyceride or phospholipid. So you have a common molecule which is glycerol, which is linked by two fatty acids. On the other side, a phosphate, and the phosphate is also linked with a polar molecule. So you have here a polar head, not here. Just here, a polar head. And here you have a hydrophobic tail. Okay, the second type of molecules composed in the membrane is the sphingolipids. So we will see you have a sphingosine, which is a molecule with a polar hydrophobic tail here. It's also linked to a fatty acid and a phosphate group. And this phosphate group is linked with another polar molecule, which is an amino alcohol. You can have also this kind of molecule, but the common structure of this molecule composed by the membrane lipids, it's always a polar head and hydrophobic tail. So let's start by the structure of the fatty acid. So the fatty acid, you always have a carboxylic group. So acid carboxylic acid, sorry, in English. Carboxylic acid. This is this part. And you have something with carbon and hydrogen, so it's hydrophobic. And you have two kinds of hydrophobic tail. You have something saturated, it means without any double bond. And you can have here, when you have a double bond, it's what we call unsaturated. So you have two kinds of fatty acid, the saturated one and the unsaturated one. Okay? You have always the polar head. Polar head. And the hydrophobic tail. Here I would. Okay, so we will see after the other molecules. So for the glycerophospholipid, so you have glycerol. This is these molecules. So we have this molecule, which is called glycerol. So this glycerol has 3 alcohol groups. In the first alcohol, you have a fatty acid linked by an ester group, ester function. So in the glycerol, you have 2 ester function, and that's why you have the link between the fatty acid and the glycerol. On the other side, you have the phosphate, which is linked to a X group. It's an organic group, and it can be an amine, amino acid, an amine, and depending on the X group, you have several names, okay? Several glycerophosphate lipid class. So you have the phosphatidylethanolamine, phosphatidylcholine, phosphatidylserine, and so on. So you have the serine here, the choline here, and the ethylamine here. Okay, we have the polar head here, and the hydrophobic tail always. So in this table, you have example of fatty acid and how we can name them. So as I said to you, you have 2 kinds of fatty acid, the saturate one, so without any double bond, and the unsaturated one. Okay, so for the saturate one, the name is always the number of carbon and 0 because there's no double bond. Okay, so for example, the lauric acid, you have 12 carbon, but no double bond, so it will call 12 0. Okay, for the last one, cerotic acid, you have 26 carbon and no double bond, so it would call 660. Okay, when you have a unsaturated fatty acid, so you have several double bond. When it's one, for example, the 14 one, it's because you have 14 as carbon and 1 double bond, and you have where is located the double bond, it's located at the carbon 9. So if you count from the carboxylic acid, it's the first carbon, the carbon 9 is the double bond, it's between the carbon 9 and carbon 10. Okay, for the 18,2, it means that you have a fatty acid of 18 carbon with 2 double bonds. The 2 double bonds are located between the carbon 9 and 10 and 12 and 13. Okay, and so on. For the cis, what it means, the cis is the stoichiometry of the double bond. So it means that the 2H, it's in the same size, and it's you can see the trans also. It means that the 2H are in 2 different directions. Okay, you know that this stoichiometry. So this is this kind, the cis fatty. It means that you have the double bond here, and you have the two H in the same direction, and the trans, you have the two H in the different direction. And it's very important to have saturate or unsaturate, because it will have influence to the melting point, and we will see to the fluidity of the membrane. So when you have saturated fatty acid, hydrocarbon tail, it will interact through relatively strong London force. London force is just like a van der Waals interaction. Okay? Because you have a lot of contact between the tail, you will have a lot of van der Waals interaction, you will have a high melting point and high boiling point. When you have a cis double bond in the unsaturated fatty acid, this cis double bond, this fatty acid interact less efficiently because of their shape. So you have less van der Waals interaction, so the melting point value will be lower, and also the boiling point value. Okay? It's like you want to stack. It's very easier to stack something with a rod than something which can be spheric. Okay? So that's why you have less interaction in the cis double bond and saturated fatty acid. After that, so usually in the glycerophospholipid, you will have one tail with saturate, so one fatty acid, one saturated fatty acid and one unsaturated fatty acid. The second kind of molecules presents in the membrane, so it's the sphingolipids. So in this sphingolipid, you have the sphingosine, which is the blue block. Okay, so you have a sphingolipids with link to another fatty acid. So in the sphingosine, you have already a hydrophobic tail with this hydrocarbon tail. You have another fatty acid, which is linked this time by here an amide group to the sphingosine. So in the glycerophospholipid, you have ester group. In the sphingosine, you have amine group. And also you have on the other side, the R group, which gives you some different families. So if it's H, it's called ceramide. It's phosphocholine, which is this molecule. You will have sphingomyelin and so on. And you have a lot of sugar at the surface. We will see that. But you have always, it will be here your hydrophilic tail, head, and here always the hydrophobic tail. Okay, so one fact that the sphingolipids are site of biological recognition on the cell. So for example, for the blood group, you know what is your blood group? A, B, or 0? So, for example, me, I have a B blood group. Usually, as in people has a B blood group. So these sphingolipids are the determinant of human blood group. So you see you have the sphingosine, the fatty acid, and linked the R group of the sphingosine will be sugar. So you have glucose, galactose, and so on. But in the presence of galactose of other groups, you can have O group, A group, and E group. Okay? No question? Okay. The third type of molecule in the membrane cell, in the cell membrane. So this is sterol. There are structural lipids present in the membrane of most eukaryotic cells. Their characteristic structure is the steroid nucleus consisting of 4 fuse rings, 3 with 6 carbon and 1 with 5. Okay, so you have A, B, C. It's a ring of 6 carbon, and D, it's a ring of 5 carbons. Okay, you can have another hydrophobic tail, but you always have the polar tail. So it's also the sterol, it's also antipathic molecules. So one of the most known sterol is the cholesterol. Is the major sterol in animals' tissue. Its non-polar hydrocarbon body is this. So you have the 3, 6 carbon rings, the 5 carbons, and an hydrophobic tail. And you have an alcohol group, so it's composed of the polar head. And you can find other sterol in depending on the, for example, you have the stigmasterol. You can find this sterol in plants, and ergosterol, you can find this in fungi. So cholesterol is for animals. Ergosterol, fungi, and stigmasterol, plants. So we know that these molecules, so glycerolphospholipid, sphingolipid, and sterol, are amphipathic molecules with a polar head and a hydrophobic tail. So when they are summed together, they make form a lipid layer. So you have one monolayer and other monolayer, and you have several processes. So you have the rotation of the phospholipid, okay? You can have what we call the flip-flop movement. It means that one phospholipid on the top monolayer can go on the bottom monolayer. Indeed, it's something very rare. It happens it's occur one by month. Okay, so let's say that it's never happened. And you have also a lateral diffusion. Okay, so it means that the phospholipid has a movement inside its monolayer. So you have 100 lateral diffusion by second. So we said that the lipid monolayer is a two-dimensional fluid. Indeed, we will consider the movement on for each monolayer. So we will talk about the membrane fluidity. So the hydrophobic hydrocarbon tail usually behave as liquids. Hydrophilic phosphate head, the polar head, act more like a solid. So the membrane is truly either what we call a solid or it's liquid. And we'll say that we have a gel transition with that. So we need to regulate the degree of fluidity in our body. Why? Because membrane needs to be fluid enough that the cell can move. It has to be fluid enough that the required substance can move across the membrane. Otherwise, it will be impermeable and no component, no nutrient can cross the membrane. But if it's too fluid, the membrane could not efficiently restrict the movement of substrate across itself. So, as I said, you have two phases, the gel, so the solid ordered phase, and the liquid, so we call it fluid. The liquid is the disorder phase. Okay, so liquids, we can have movement, bilateral movement, and in the solid, you cannot have any movement. So lipid fluidity, it's temperature sensitive, okay? We measure what we call a phase transition point, okay? The phase transition point is the temperature for which 50% of the membrane is like a solid and 50% of the membrane it's like the liquids. So we consider that the transition temperature, Tm, is the transition between the gel to the liquid to the fluids. So it will depend on the fatty acid nature. Indeed, if you see that, so it's a French table, maybe you can. So this is the melting here. Melting transition of the fatty acid. Okay. And what we observe that for the saturated fatty acid, so which has no double bond, 0, 0, 0, the melting temperature increase with the number of carbon. Okay? And so the transition temperature increase with the number of carbon, because when you have more carbon, the van der Waals interaction will increase. Okay? Let's see, when you have the same number of carbon here, but here it's saturate and here it's unsaturated, okay? So you have a double bond here. What we have, when you have a double bond, you will decrease the van der Waals interaction. Remember, because when you have completely saturated fatty acid tail, you can stack the rod very easily. But when you have double bond, the shape of this tail, it's more like something spherical, not spherical, but something. So it's mean that the van der Waals interaction between the tail will be less important. So that's why when you have a double bond, the melting temperature decreases. So the transition temperature decreases also. Okay? And we have the same when you have 2 double bond and 3 double bond. Okay? So the number, with the number of double bond, the temperature will decrease. Okay? So we can see that the transition temperature is related to the melting temperature of the fatty acid. You have the same behavior. It means that you have, when this melting temperature increase, the transition temperature increase in the B layer, and so on. So for example, we can have here, we measure here the fluidity of the membrane modelized by 2 phospholipids. So the DMPC, so it's made with saturated fatty acid with 14 carbon, and DSPC is also saturated fatty acid, but this time with 18 carbon in the tail. Okay, so we see that the transition temperature increase when the B layer is formed by DSPC compared to the B layer composed by DMPC. Okay. So how can we measure the membrane diffusion? We can use a technique which is called FRAP. So it's fluorescence recovery after photobleaching. So how we do that? We will put fluorescence molecules in the membrane. So that's why you can see something green upon the laser light. What happened? Your organic molecule will be photobleached. It means that when you have a laser, the fluorescence of your molecule will decrease because the light of the laser is too strong. Okay, it's called the photobleaching. So at the point at time zero, you will not have any fluorescence because of the photobleaching by the laser. But after that, because you have membrane diffusion, it means that you have movement in 2D in the membrane, you will recover the fluorescence. So we will measure the fluorescence intensity against time. So at this time, so it's T equals 0. This is the photo-bleaching by the laser. And after that, you will recover the fluorescence. So you will measure the fluorescence of the time. And depending on this curve, you can measure the fluidity if the membrane is more or less fluid. Alors, tuk. Yes. Just for this slide, it's to remind the cholesterol. So you have the polar head, the steroid ring, the hydrocarbon tail, hydrophobic tail. So you have the thickness of this cholesterol. So it's here, it's 3 nanometers of the thickness of the lipid membrane. It's around 6 nanometer. But just to say that the B layer are asymmetric. It means that one monolayer, the composition of the, for example, the top monolayer is different from the bottom monolayer. Okay, so it's between the extracellular space, the monolayer, which give the extracellular space is different from the monolayer in contact with the cytosol. Okay, so we will see that it's very different and it will give us some potential gradient. So the role of cholesterol. So just always the head, the hydrophobic tail, and this is stacked like this. That means that the cholesterol is between the phospholipid, glycerophospholipid, and also the sphingophospholipid. And so what happened when we measure the diffusion, so the fluidity of a membrane modelized by DMPC in the presence or in the absence of cholesterol, we obtain this kind of curve. So in the absence of DMPC, we have low fluidity at low temperature and high fluidity at high temperature. The cholesterol will increase the fluidity of the membrane at low temperature and decrease the fluidity of the membrane at high temperature. Why? Because at high temperature, this is this case, high temperature. So this is 1 and 2. At high temperature, the presence of cholesterol in the membrane restricts the movement of phospholipid and other molecules. This reduces the membrane fluidity because the cholesterol is something rigid because of the fuse ring. Okay, so the structure of the cholesterol is very rigid. So when you have a lot of cholesterol, because it's rigid, the phospholipid cannot move to, and it reduces the membrane fluidity. At low concentration, at low temperature, this time the presence of cholesterol disrupt the regular packing of the hydrocarbon tail of the phospholipid. So it will increase the flexibility and increase the fluidity of the membrane. Okay. Okay. So that's why it's very important to control the cholesterol ratio in our body, the cholesterol percentage in our body. Okay. To have a membrane which is more or less fluid and which can allow the transport of some molecules. Okay, so that's why we have cholesterol. Okay, so we see the phospholipid. Now we will see, I told you that the second component of the membrane will be the proteins. So you have two kinds of membrane proteins. You have integral membrane, the yellow one. So it interacts with hydrocarbon region of the B layer. It is called also integral membrane. And you have the peripheral membrane or extrinsic membrane in the blue one, the C and D. This membrane binds to the surface, usually of integral membrane or with the polar head of the membrane. So to know if you have integral or peripheral membrane proteins, usually we try to solubilize by different conditions. So for example, when you can extract your protein by a solution of high ionic strength, so it means that you have electrostatic interaction. So usually you can remove the C and the D by using high concentration of salt, because it's electrostatic interaction between the polar head and the peripheral membrane. But when you have to extract the membrane proteins, you need to use detergent or organic solvent. Okay, so to remove the B and C, you can use, for example, 1 molar of chloride sodium. And to remove the A, B, and C of this membrane, you should use detergent or organic solvent. So when you want to purify this membrane proteins, you have to extract them from the membrane. So some proteins associate with membranes who covalently attach hydrophobic groups. It means that you know that we have on the phospholipid, we can have sugar like sphingolipid. On the polar head of the sphingolipid, you can have a change of hydrohydrate carbon, so sugar. And this can be linked to proteins. Okay. This other protein can have also linked to a fatty acid, for example, by aminamide group. And this fatty acid can interact with, because they have a hydrophobic tail, it can interact with the membrane proteins. Okay, so you have the name of some proteins. I told you that after the translation of your protein, you can post-translation process. So you can have your protein, it can be attached with a fatty acid, just like, for example, the N myritoyl glycine, farnesyl cysteine, and so on, would be attached to different amino acids of the proteins. Okay, so that's why you can have some membrane proteins. Protein can span the membrane with alpha helix. So you can have integral membrane with several alpha helix. So this is the structure of the bacteriorhodopsin. And what is the role of these molecules, of these proteins? We will see. You have inside something hydrophobic, and outside you have something hydrophobic. Sorry, in the black it's hydrophilic. Hydrophilic. So, sorry for that. So it means that the outside of the protein, okay, of the helix can interact with the hydrophobic tail of the phospholipid of the membrane. And you have a channel made by the alpha helix, which is this time hydrophilic, and he will allow the transport of hydrophilic molecules. Okay, so in yellow, you have the hydrophobic amino acid, and in pink you have the hydrophobic amino acid. So the pink amino acid will be inside the proteins, and the yellow amino acid will be outside the protein and in interaction by hydrophobic interaction with the tail. Okay? You can have also channel formed by beta strand. So this time always you have outside the hydrophobic part of your protein. Hydrophobic. J'arrive pas à l'écrire. Hydrophobic. So this is the yellow one. And inside you have always here an hydrophilic, and you can have then a channel which allow the transport of hydrophilic molecule, because the hydrophilic molecule will channel. Okay, so you can have the sequence. This time it's a porine, and you remember that in the beta strand you have one amino acid on one side of the beta sheet and the other on the other side. So you have hydrophobic, hydrophobic, hydrophilic, hydrophobic, hydrophilic, and so on. So you have inside the hydrophilic and outside the hydrophobic. Another example of membrane proteins So you have this time a membrane, which is not integral. Only 3 alpha helix are in interaction with the membrane. Okay, so if we focus on these 3 helix, you have hydrophobic amino acid side chain. It can interact with this membrane. So why these proteins, so the prostaglandin H2 synthase is attached to the membrane? Because its substrate is arachidonic acid, which is a fatty acid, which is a component of the phospholipids. So after hydrolysis of a phospholipid, this arachidonic acid, which is the substrate, can go to the active site of the proteins by an hydrophobic channel. Okay, so the fact that the membrane is attached to the membrane, the fact that this protein is attached to the membranes allow that this substrate can go to the active site by the hydrophobic channel and avoid the contact with the water because this molecule is hydrophobic. Okay. So how to predict the topology of a membrane proteins? In fact, we can plot what we call hydropathy plot. This is this. Hydropathy plot. So how we can do that? We have the free energy of transfer of each amino acid. Okay, the free energy, so it's the delta G of an amino acid in hydrophobic solvent. We measure this delta G, so the free energy of this reaction. It means that the transfer of this amino acid from an hydrophobic solvent to water. Okay, so if the delta G is positive, the amino acid is hydrophobic. And if the delta G is negative, the amino acid is hydrophilic. So in this table, you have in this part the hydrophilic amino acid or polar as you want. And here you have the hydrophobic amino acid. Okay? So when we have the sequence of the proteins, we can have the hydropathy plot. My hydropathy plot. So we measure the hydropathy plot for each amino acid, and we can see that, for example, here we have something very hydrophobic. So it corresponds to the alpha helix, which cross the membrane. Here you have for the glycophorin only one alpha helix. For the other amino acid, you have A, B, C, and D. 1, 2, 3, 4, 5, 6, 7. You will see that you have 7 alpha helix. So that's why you have 7 alpha helix in the bacteriorhodopsin. But for the purine, we cannot see nothing because you remember that for the beta strand, you have one amino on the top and one amino on the bottom of the sheet. So we cannot have any behavior. We cannot see clearly secondary structure, which is hydrophobic or hydrophilic. Okay, maybe, no. So I thought that it was a coffee break, but not, we still have an hour. So I can continue. Yes, I have only okay. Before the coffee break, we can talk about the membrane transport. Okay, the protein-free lipid bilayer are highly impermeable to ions. Okay, so if you see you have the synthetic lipid bilayer, all the hydrophobic molecule, small hydrophobic molecule can cross very easily the lipid bilayer. For the charge, for small molecule, uncharged or polar, this is less easy. For the large, uncharged polar molecule and ion, it's very difficult to cross the membrane without any proteins. Okay, so you have the same scale, another scale here. You have the diffusion flux of the molecules across a bilayer, lipid bilayer, and you see that for water, it's high permeable, but for ion, cation or anion, you have very low permeability. Okay? So that's why we need proteins to cross the membrane. So we have 2 classes of membrane transport proteins, the carrier and the channel. So the channel, okay, so you have channel and carrier. Okay, the channel interact with the solute, the molecule you want to transport, to be transported with less interaction. Okay, they form aqueous sport that extend across the lipid bilayer. It means that you have a pore between the lipid bilayer. Okay. In the carrier proteins, you have not a pore. You need a change in the conformation of the protein to allow the transport of the solute. Okay, it means that the solute binds to the specific proteins to be transported. Okay, and after there undergoes a series of conformational change to transfer the bound solute across the membrane. Okay, we have 2 types of transport: the active transport and the passive transport. The passive, so for channel, it's always passive transport. Okay, so for carrier proteins, it can be active or passive. Passive it needs for active transport, it means that you need an external source of energy here. We will see that it can be the hydrolysis of ATP, but also another energy, kind of energy. Okay, so it means that the passive transport will go with the concentration gradient. It means from the high concentration compartment to the low concentration compartment. Okay, so it would the molecule will be transferred spontaneously down the concentration gradient. Okay. On contrary, the active transport will go against the concentration gradient. Okay, so the molecule will be transported from the low concentration in this compartment to the high concentration compartment. Okay, so that's why it needs some energy. So let's see first the passive transport. So it's downhill diffusion and it's facilitated by membrane proteins. So for example, a simple diffusion without transport, you will have this kind of energy. And with the transporter, you will decrease the energy. So it means that it's a catalysis. Okay. So it's like an enzyme indeed. Okay. We can measure the rate of transport against the concentration of transport molecule. And we have this kind of curve. And this kind of curve, it's like enzymatic curve. You know that probably. It's a Michaelis-Menten like curve. Okay, so that's why we can measure a maximum rate and a Michaelis constant. So the Michaelis constant will indicate the specificity of the substrate against the transporter and the rate, maximum rate. Okay, so the transporter have the same behavior than the enzyme, but he cannot transform the substrate to another molecule. He just transports the molecule. This is the same molecule inside and outside. Okay. So here you have a channel, and here you have a carrier with a conformation change. So you have what we call the ping pong conformation shell. Pong is because of outside. It means that the molecule will from the outside will interact with the carrier. And after the conformation shell change, the molecule will be inside the cell. So, for example, you have the glucose permease. So you have the glucose permease. In the blood, you have a concentration of 5 millimolar, and the intracellular concentration of the glucose is less than 5 millimolar. So that's why you have a passive transport. from the high concentration to the low concentration compartment. You have a protein which is called glucose permeable, okay? And so you have this kind of equation like Michaelis-Menten mechanism. You have the solute outside, you will form a complex, and after you have the change in the conformation, and after the release of the solute inside and the transporter, okay? You can measure, we can plot also the rate of the transport against this equation. So again, the Michaelis-Menten equation, you know that. So we can have obtain from this plot of this plot the Vmax and the Tm. Okay, you're familiar with the Michaelis-Menten, I hope. Okay, last slide before the coffee break. Maybe what this. Okay, so we have the co-transport. Indeed, some carrier proteins simply transport a single solute from one side of the membrane to the other side. Okay, so if you have only one solute, a single solute transported, it's called uniport. Okay, in some more complex kinetics, we will see after that, after the coffee break, we will have a coupled carrier. It means that we have a transport of a second solute, okay? So one solute strictly depends on the transport of, the transfer of one solute strictly depends on the transfer of a second, okay? So if the second solute goes in the same direction, so from the first and the second one goes in the same direction, it's called the syn port, okay? On the other side, if the transport of the second solute in the opposite direction of the first one, it will go antiport, okay? And we will see the co-transport is very important in the active transport of some proteins, okay? So just before the coffee break, we can make a quiz online. Alors, I will give you the code and start. Let's go. I told you that the thickness of the plasma membrane is between 4 and 10 nanometer. Okay. Yes, indeed, the one who will diffuse the less quickly, it will be ferric ion because it's ion, okay? Glucose, it's polar, urea, it's polar, so ethylene is the less polar, it's the most hydrophobic molecule, so he can diffuse, be transported more easier. Third question. Yes, the membrane proteins are not covalently bound, not always covalently bound to the lipids. Last question, I think. No, four. Yes, it was difficult. So it decrease fluidity at high temperature and increase fluidity at low temperature. So this is the last answer. So this is the last question. Yes, so the polar bear is living in region with low temperature, so he needs to have a fluidity in of the membrane. So to do that, he needs saturated phospholipids. So I think our winner will be Lynn. Maybe, probably. Yes. So who is Lynn? Hello, congratulations.
Thank you.
So we can make 10 minutes of coffee break, okay? And after I will finish the lecture and we will have exercise. Let's go. So Zoom. Okay. So now we will see the thermodynamic point of view for the membrane transport across the membrane, sorry. So for uncharged molecule, the free energy, so the delta G, from the compartment 1 to the compartment 2 depends on the concentration gradient across the membrane. You know, if you have a spontaneous process, the delta G, sorry, I don't have the same. Just, yes. So if you have something, if you want to have something spontaneous, the delta G should be negative. So it means, so you will have a spontaneous process if the C2 is lower than the C1. It means that for a neutral molecules, you will have the transport will be from the high concentration compartment to the low concentration compartment. It's called the passive transport. Okay. For the charge solute, indeed, because of the asymmetric component of the membrane, I told you that the monolayer composition are not the same. Okay, from the cytosol part of the outside part. So you have what we call a membrane potential, as well as a chemical concentration gradient, as usual. So the delta G should be also negative to have something spontaneous. And the delta G, it's this time related to the chemical concentration gradient. This is this part, okay? But it is also because of the presence of the membrane potential. And in this, you will have the Faraday constant, which is uh, 96,500. Sorry. The Z is the charge of the molecule. So if it's positive, it's +1, for example, and if it's negative, it's if you have an ion, you will have a Z negative. And this is the potential of the membrane. The potential of the membrane is because you have difference in the charge between the outside and the inside monolayer, because you can have something positive charge in the outside and negatively charged in the inside. So you will have a potential of membrane. So what we call the resting potential, it's when the delta G it's negative because it's equilibrium. And so the resting potential, it corresponds to this, okay? R is the gas constant. So it's 8 point, it will be in kilojoule, in joule, sorry. Joule, molar -1, Kelvin -1, T will be in Kelvin. Don't forget that temperature in Kelvin, okay? So we will have exercise about that, okay? So we have active transport result in some movement against a concentration gradient. So the passive transport is down a concentration gradient. For the active transport, it's against the concentration gradient. It means that you transport something from the low concentration compartment to the high concentration compartment. And you have two kinds of active transport. The first one, it's a primary active transport. So the energy, so because you transport something against a concentration gradient, for example, for the potassium, okay, you will transport from the low concentration to high concentration. You need energy, and the energy given by the hydrolysis of ADP will allow the transport of the potassium from low concentration to the high concentration compartment, okay? So the hydrolysis, you should know that the hydrolysis of ATP, it means ATP for the reaction from ATP to ADP. The delta G 0, it's around minus 30.5 kilojoule per mole, okay? The secondary active transport, you need another source of energy. It's not the hydrolysis of ATP. It will be the transport of something from the high concentration to the low concentration. We will see that in some examples, okay? So the first example of primary active transport is the transport of sodium, potassium, ATPase. So when we see the sodium uptake, okay, it depends on the temperature and it depends on the presence of potassium, okay? So if you don't have any potassium, the sodium cannot be transported. And if the temperature is low, the sodium cannot be transported. It means that you need ATP, because the ATP hydrolysis depends on the temperature. And here it means that you need potassium. So it's a co-transport, okay? So potassium needed and ATP hydrolysis needed also. Okay, so how it happened? So you see that first you have the concentration the cytosolic concentration of potassium and sodium. So it's higher for the potassium inside than outside. And for the sodium, it's lower in the cytosol than in outside. Okay, so we will transport against the concentration gradient, the potassium from outside to inside, and the sodium from inside to outside. So it's both an active transport, okay, because it's against the concentration, and it is what we said it was an antipore, because the two solutes transported are in opposite direction. So how it works from the sodium potassium ATPase? First step is the bending of the cytoplasmic sodium to the protein. Okay, so it stimulates the phosphorylation by ATP. So this is the hydrolysis of ATP. You will have phosphorylation of the protein ATPase. So the phosphorylation will cause the change in the conformation. So then the conformational change release the sodium to the outside, and then the extracellular potassium can bind to these proteins. Okay. The potassium bending allows the release of phosphate. You have a change in the conformation. You restore the original conformation, and then the potassium is released into the cytoplasm, and the sodium site are receptive again, and the cycle can repeat. Okay, so this is the source of energy, is the hydrolysis of ATP. So it's a primary active transport. In the case of the secondary active transport, so you have the solute A will be transport from the high concentration compartment outside to the low concentration of the compartment inside. So it means that the delta G, the free energy of the solute A transport, is negative. Okay. So this for A, a passive transport. For B, we want to transport B from a low concentration compartment to a high concentration compartment. So the delta G, this transport is not spontaneous because the delta G will be positive. Okay. So to transport B, the solute B, from the outside to the inside, we need a co-transport, because we will have the overall delta G of the transport of A and B will be the delta G of A plus the delta G of B, and because it will be negative, the transport for A and B will be allowed. Okay, so this is the way to allow the transport of B from a low concentration to a high concentration compartment. Okay, so you have in this table the co-transport system driven by the gradient of, usually it's called sodium or proton co-transport. So you have the co-transport solute and the transported solute. So in this case, we have a steam transport because it's in the same direction, but you can have also an anti-transport. So it means that the solute are transport in the opposite direction. Okay. The last transport, it's for very high, very with molecule with high mass, like solid particle or extra fluid, extracellular fluid. You can have several types of transport, which is called endocytosis. It means that the plasma membrane, because of its fluidity, will form a phagosome, a vacuole, to transport something with high molecules. So indeed, the plasma membrane is not static. It's always in movement, and you will have formation of vesicle, vacuole, and so on. And you have also something which will be specific. So it calls this receptor mediate endocytosis. So for example, is the transport of iron. Iron, you know, sorry, how can I? Yes. So it's iron 3, iron ferric iron, you know, it's an iron, so it cannot be transport in the membrane without any proteins. And also iron ferric iron, it's insoluble in water. That's why you have a proteins which is called transferrin. So TF is transferrin. So transferrin is the protein which which transports the iron, because iron is insoluble under physiological condition. And the iron acquisition from the cell, it's mediated by the transferrin receptor endocytosis. So you have the apotransferrin without iron. Iron will interact with the apotransferrin to be iron saturate transferrin, holotransferrin. This holotransferrin can interact with the transferrin receptor. Okay, so the interaction between iron transferrin and its receptor will form the endosome. Okay, the membrane will be fluid and form endosome. So the iron bond transferrin is then internalized in cell the receptor mediate endocytosis. So following the formation of the endosome by the proton pump, the endosome media will be acidic, and then the iron will be released from the transferrin. Okay, and with other transporter or channel, you have the release of iron in the cytoplasm, and then the transferrin receptor adduct will move to the extracellular space, and you can make another cycle of iron transport. Okay, and the last slide is this. On the other side, the exocytosis. This time when you have formed something in the cell or in the nucleus, you can remove what we synthesize in the plasma, in the cytosol, by this time exocytosis. Okay. Do you have any question about this lecture? Maybe we will see with the exercise. Okay. Hello. Okay. So I have some exercise. Alors, okay, can you see the slides? Okay. So in the first exercise, consider the fatty acid below. So you remember that the first number corresponds to the number of carbon. So it means that in the first molecule you have 16 carbon, and the second number corresponds to the number of double bond. Okay. So in the first molecule you have saturated fatty acid. You have no double bond. Okay. In the second molecule, you have one double bond and it's between the carbon 9 and 10. Okay. So you have the melting point and you have to attribute this melting point to the corresponding fatty acid and tell me why. Are you there?
Yes.
So
Okay. So in my opinion, I think the melting point minus 5 degree will correspond to the C18
yes, yes. I told you then when you have double bond, you have in degrees in the melting temperature. So this is minus 5 degree. Okay, so we have this one, the 17.
0 degree will correspond to C16 one.
Yes. So the 13.
13 will be C18 one.
Yes. Okay. And after, when you have no double bond, it depends on the number of carbon because more you have carbon, more you have van der Waals interaction. So you will increase the melting temperature. Okay. So the 17 will be C18 and the 0 will have a melting point at 63 degrees. Okay. So for justify, I told you, so when you have more carbon in your hydrocarbon tail, you will increase the van der Waals interaction, so you will increase the melting point. After that, I told you that when you have a double bond, you will decrease the van der Waals interaction because of the shape of your molecule. And the more you have double bond, the lower is your melting point. Okay. Second exercise. You have triglyceride and a phosphatidic acid. So you have in this molecule glycerin, okay, this is this part. Glycerol, pardon, and also this. Okay. You have in this glycerol, in this molecule, you have here the fatty acid. So it's hydrophobic tail. Okay. Or the fatty acid linked to the glycerol are hydrophobic tail. Here also you will have hydrophobic tail. Even if the change are less longer because you have only 6 carbon, but it will be hydrophobic. But the more important that you have a phosphate group which corresponds to a polar head. Okay. So in the benzene, you have difference between water and benzene. Benzene, water, you know that it's a polar solvent. And benzene, it's an apolar solvent. Okay? So you have these two molecules. It's dissolved in benzene and strike with an equal volume of water. So we try to extract this molecule with water from the benzene. When the two phases are separate, which lipid is in high concentration on the aqueous? Explain. With which molecules stay in benzene and which molecules will go to the water? It depends.
Because the acid phosphatidic, they have a polar head.
Yes.
So maybe they can go to the polar solvent like water.
Mm-hmm.
And so the remain will be in the benzene.
Mm-hmm. So this is we already told that when you have polar groups, you will have interaction with polar solvent, and when you have hydrophobic groups, you will have more interaction with the apolar solvents. In French, we said zut, qui se ressemble s'assemble. You understand? It means if you look like, you will stay together. If you have the same behavior, you will stay together. So this has a polar head, so we will stay in water. high concentration in water, and this one has only hydrophobic tail, so will stay in benzene. Okay? It depends on the interaction with always. Okay. So we have in exercise 3 proteins, which is a receptor, and he has an integral membrane proteins with a molecular mass of 64 kilodalton, and that is believed to span the membrane several times. So show that a protein of this size is capable of spanning the membrane several times. Tell me how to do that.
Is that because the protein combine 7 alpha chain?
Yes, but you have to, if the number of amino acid, the molecular mass of the protein correspond to 7 indeed. So for example, let's say that the thickness of the membrane is around 7 nanometer. Okay. So if you have the thickness of 7 nanometer, how many amino acids you will have in the alpha helix? You remember? Indeed. How many amino acids you have in the protein with the molecular mass of 64 kilodalton? You know the molecular mass, the average of an amino acid. The average mass of an amino acid. What is the average mass? Sorry, you have a discrete. 110 kilodalton. It's not kilodalton, it's dalton. Okay? So in that if you have a molecular mass of 64,000 dalton for protein, it means that you will have around 64 over 110, 582 amino acid. Okay? Yes. And do you remember the characteristic on the alpha helix? How many amino acids you have by turn?
.6.
3.6, correct? And what is the height of the turn?
5.4 angstrom.
Yes, 5.4 angstrom. It means that you have 0.54 nanometer. Okay. So for a thickness of 7 nanometer, how many turns do you have?
Uh, 13 turns.
Yes, 13 turns. So 13 turns correspond to how many amino acids?
Uh, 47.
Yes, 47, correct. So if you have 7 alpha helix of 47 amino acids, so you need, it means that you need 320. So I said counted for 329 amino acids for 7 alpha helix, right? So this is less than the 782 amino acids of the proteins. Okay, so it's allowed for this protein to have 7 alpha helix spanning the membrane. Okay? Okay. So the second question, if you were giving the amino acid sequence of this protein, how would you go about predicting which region of the protein from the membrane spanning helix? So for that, we need the hydropathy plot. Okay, and if I draw this, I will have probably 7 times the plot of 7 times et 1, 2, 3, 5, 6, 7. And here you have hydrophobic amino acid, hydrophobic, and here hydrophilic. And we need something hydrophobic to interact with the membrane. So it means that you have the alpha helix A, B, C, D, E, F, and G. So the 7 alpha helix. Okay. Do you have question? No? Okay. Okay. So So at pH 4, we have 4 proteins, A, B, C, and D, of 18 amino acids arranged in an alpha helix secondary structure, and they are represented in the presence of biological membranes according to the scheme below. Okay, so you have to tell me which sequence corresponds to which amino proteins and why. So you have protein composed with arginine R and isoleucine. Arginine is hydrophobic or hydrophilic. Arginine R is arginine hydrophobic or hydrophilic?
It's
Polar or
hydrophilic.
hydrophilic because it is positively charged. Okay, and it's isoleucine, it's hydrophobic. So if we take the sequence 1, okay, you remember if we have a top view of an alpha helix, if I start with the R here, I will have 100 degrees for the second amino acid. So R is here, and after I will be an I, R, R, I, and so on. So après ça. R, okay. Okay, so this top view of this helix show us that we have here a charge or polar side. On the other side, we have something hydrophobic. So it's called what we say a amphipathic helix. Okay, so it means that one side of the helix is charged, the other side of the helix is hydrophobic. So the sequence 1 corresponds to which protein?
Protein I.
Yes, so it would be the A because here you have the side which is ionic and the side which is polar will be outside the membrane. Okay, so for the other, sequence 2 corresponds to E, C, or D.
Protein C.
Mm-hmm. Sequence 3. It will be something charged. So it will be soluble in the cytosol.
D. For D.
D, yes. So the last one will be B, and it will be an integral proteins. Okay. Tell me if you have question. Okay. No. So I need you, and you have to use your calculator. So we have a concentration inside of sodium, and okay, and we want to know if we want to calculate the free energy of the transporting of 1 mole of delta of sodium out of the cell. Okay, so for that we need to use the formula of the free energy. So I remind you, so the delta G from inside to outside, it's RT logarithm of the ratio between concentration of outside over concentration of inside plus Z F potential outside minus potential inside. Okay, so don't forget, here we have the concentration 12 molar, outside 155 millimolar. The potential outside minus inside negative related to outside. Okay, so the potential of the membrane will be plus, sorry, this will be plus 17 millivolt. So it corresponds to 0.07 volt. Don't forget that the potential should be in volt. Okay, so you have to calculate the delta G. Let's say that the R it's the F it's normal. The temperature should be in Kelvin. The charge of the molecule will be +1. Okay. Calculate and tell me if it's allowed to transport the sodium from inside to outside.
Teacher,
Yeah.
what is between T and the concentration? The equation. I asked about the equation. I don't know what is between the temperature and the concentration.
The temperature, it's in the formula. You have RT, right?
Oh no. Okay.
So you have the temperature, the gas constant, and you have the logarithm of the, say, what is the other question? It's okay?
Yeah, it's okay.
Okay. And it's not log, it's logarithm. So it's logarithm Nepérien. Okay? It's not what I found. Do you have another result? So it's logarithm. It's not log, okay? It's logarithm Nepérien, ln. Yes, I found this. So I found what is important, it's the sign of delta G. Okay, so it's positive, and the value it's, yeah, 13.2 kilojoule molar minus 1. Okay, we find that. Okay, so the most important is the sign of the delta G. So you have delta G, which is positive, so it's not a load. It's not a spontaneous reaction. We need something, energy, to permit the transport of sodium from inside to outside. Okay? You have any question? So we will use always this equation of the delta G, and you have to find me in this exercise the delta G for all these ions: potassium, chloride, sodium, calcium. Be careful for the calcium, the charge will be 2, okay? And for the chloride, it will be -1. Be careful of this, it will be minus 0.006 volt. It corresponds to the potential of inside minus outside, okay? Because inside it's always negative. And you have to sorry, is the neutrality respected? So if we measure the concentration of ion in the intracellular medium, you can see that the electron neutrality is not respected, okay? Because the negatively charge is not correspond to the positively charge. So indeed, so the answer is no. So what are the waterproof uncharged molecules which are not mentioned in the exercise and which are responsible to participate in the electron neutrality? So it will be proteins. Okay? And you have to calculate the delta G from inside to outside. Okay? So if it's positive, it means that the ion go from outside to inside. And if it is negative, so it means that it's a reaction which is spontaneous. So it means that the ion will go from inside to outside. And we use this equation, I'll give you, so RT, okay. Be careful, here it's phi I out inside minus phi outside, and in this equation is the opposite, okay? So maybe you can do that for homework and you calculate for each ion, yes? Otherwise we can calculate this, but maybe we can finish by this exercise. So in this last exercise, you have a co-transport, a syn port. It means that it will goes in the same direction, okay? And you have a syn port of glucose and sodium. So the concentration of glucose is 25 times greater inside than outside. Okay, so if we have, I'm sorry, the concentration, of glucose inside we have 25 concentration of glucose. For the sodium, the external concentration of sodium was only 10 times greater. So if we have the concentration of sodium inside, we have outside 10 times the concentration of sodium, okay? So it means that this is the glucose outside, glucose inside, sodium inside, and sodium outside. Okay? So, indeed, we have to measure the delta G of the synport. That means the delta G of the transport of the glucose and the transport of the sodium. If we have a global free energy negative, it means that the synport is allowed. Okay, so we have to measure the delta G of the transport of the glucose from outside to inside. This is okay. So glucose is a non-charged molecule. So the delta G, it will be RT logarithm the glucose inside over glucose outside. So tell me if it's the value and if it's positive or negative. And after that, you can calculate the delta G of the transport of the sodium. This time we have a charged molecule. So the equation is okay. We have there's no value. Let's say that this is minus 0.07 volt. Okay, and tell me if it's a violation of the law of thermodynamics. Alors, we have answer. What is the temperature? Oh, yes, let's say, yeah, let's say 37 degrees. Okay, so it's in Kelvin, it's 310 Kelvin. Okay. Sorry, I forgot to tell you. Alors, delta G for glucose, you find yes, so it's correct. You find plus 8.3 kilojoule per mole. So it means that the transport of the glucose is not allowed. It's occur only alone. Okay. And for the sodium, you find yes, the same approximately. You find minus 12.7 kilojoule per mole. So it means that it is allowed. So if we calculate the overall delta G, we find something negative for minus 4.4 kilojoule per mole. It means that this is something which is allowed. Okay? So the transport of glucose as a uniport, so only the glucose is not allowed. It will be allowed if this transport is combined with the transport of the sodium. Okay? Do you have any question? It is the end of the lecture. For today. So if you don't have any question, we can see each other on Wednesday, I think. And it will be the last lecture, sorry. It will be the last lecture. It will be about the metals in the proteins, and we will see the role of the metal in the proteins. Okay? No question? Maybe on Wednesday you will have question. You can ask me by email or on Wednesday by Zoom. Okay? I will send you the slide as usual, so I can end the Zoom. Okay? See you. Bye.